the topic I'm going to talk about is high-dimensional expanders in theoretical computer science. Now, as you know, high-dimensional expanders is a kind of a new topic, and it's emerging. So we have, every couple of years, there's a new link that we can feel a bit more secure to say high-dimensional expanders are related to computer science, but it's not yet a well-established area. So I think it's more exciting. So before I speak about high-dimensional expanders in computer science, let's talk about expanders, because expanders really are appearing everywhere, and in particular, they appear in many, many places in computer science. So what are expanders? These are networks. We think of graphs. Okay, let's see if I can do. So an expander is a graph. So you see here a network. Every node here is a person, and we have links between the people. So this is, in some sense, how we think about a graph, a one-dimensional graph. And this is the most natural way to think about an expander. It's a network that's very, very well connected. So you cannot split it into two parts. Maybe half the people, you color them green, the other half you color yellow, and without having many, many links broken between the yellow people and the green people. So that would make this graph an expander. And what's interesting is that we have expanders where every person or every node is only connected to a constant number of other nodes, and yet this strong connectivity holds. So here, I guess I wrote that, for example, you can remove many edges. So the definition of expander is when you split the nodes into two parts. But another property of expanders is that even if you remove many edges, like 1% of the edges, the network is still going to be very resilient. So you imagine that these edges were removed because some link fell, some bridge was broken, or something like that. Still, the graph will be very well connected. There will be many other paths to bypass this fallen edges. Of course, some specific nodes can be completely disconnected. That can happen, but there's still going to be a huge component that remains very well connected. So that's the most immediate, I think, way we think about expander graphs. But it's not at all the way that expander graphs appear in computer science. Of course, it's one of the ways, but there are many, many other ways. Here's another famous, Alex just talked about it, famous way in which expanders appear in a very beautiful construction of error-correcting code. So let's talk a little bit about error-correcting codes. So I guess in the background of this slide you were supposed to see a lot of zeros and ones, like a lot of bits, but somehow I don't see it. So, data is everywhere. We save our data on our hard disk. We transmit our data when we talk on the cell phone. And these are physical devices. Noise and errors happen all the time. But we cannot always afford to have some bits flip from 0 to 1. Sometimes if you talk on the Zoom, and some of the bits get flipped, so one of the pixels in the Zoom gets flipped from black to white, that doesn't matter at all. But if some bit denotes, I don't know, whether or not to do some action, like to buy stock, and it gets flipped from 0 to 1, that might be much more consequential. So we definitely don't want to afford any errors happening. And the way this is solved every day is by encoding, by using error-correcting codes. We encode all our data transmission in a way that if a few errors happen, they can be corrected. Okay, so we estimate that there's only going to be some 0.5% of errors, and then we use codes that allow us to correct this fraction of errors. Now, how would you do that? One natural way that we do it, if we're yelling to someone across and there's a lot of wind and rain, we'll just shout 3 times, and hopefully they will understand it by the 3rd time. But if you want to transmit data, okay, so I was saying that saying your message 3 times, if you want to say 0, you can say 3 times 0, and the recipient will take the majority. That will work. But it's not very good. First of all, you pay in overhead. You really transmit only 33% of the bits of your channel. And also, this only corrects 1 bit. So there are much more clever error-correcting codes that will actually only use a very tiny overhead. To transmit 1,000 bits, you maybe, of actual message, you will only need to spend another 10 or 20 extra bits. That's the kind of error correction that is considered much more feasible in real life. So what is a code? A code is like a dictionary. You take all the messages, all the 1,000-bit strings, and you encode them by slightly longer messages, such that every pair of encoded messages are a bit far from each other. Say they're pairwise far from each other at least 10 bits or 20 bits. Okay, so that the set of all encodings is the error-correcting code. And then how do we use these things? So I have a message, I encode it, I send it over. The receiver gets this message, but maybe some errors happen. So the receiver needs to look at the string and find the closest string that's actually in the code, that's a valid code word, so that if at most such and such number of errors happen, you know that they got the correct message. How do you find from the received word, how do you go back and find the closest code word? If you think about it in a geometric way, you have some geometric space of all the strings. And what you have is the initial point was here, some noise happened, so you moved, and now the receiver got this point, so they need to kind of search in this whole ball of vicinity, I don't know, 5% of the bits to find the actual code word that was sent. This is an exponentially large search space, and you need to find some clever algorithms to do it, because if you just search the entire space, it's very inefficient. And that's where different clever constructions of error-correcting codes come in, where they also come together with an algorithm for decoding. And the celebrated expander codes of Sipser and Spielman are such codes. They are codes that give you also an algorithm for decoding. Okay, so they built error-correcting codes based on expander graphs. I think if you see this whole slide, and suddenly here you say, oh, these are based on expander codes, it's not like you would expect it. What do expanders have to do with any of this thing? So I want to say something about how do expanders fit into this picture. So suppose you have an expander graph. And I apologize to those people who also were present in Alex's talk and saw a lot of this, but it's a bit repetitive. So an expander graph, we said it's like a network. You have vertices and edges. And the Sipser-Spielman code, the expander code, will just say, I'm going to look at what are the code words? They're all strings of zeros and ones on the edges that satisfy that around every vertex, some conditions are made. So every vertex looks at the edges around it and needs to have, say, the parity has to be 0. Or maybe something a bit more clever. This is an expander code. Now, how would you decode a message? So when you get a message, it's a sequence of zeros and ones on the edges of the graph. And maybe not all the parities are satisfied because there was some noise, right? Because the graph is an expander, if some bits were flipped, the vertices near those edges will usually say, look, something is wrong around here, okay? And then you can use some local search. Just the vertex will say this edge is suspicious, and this vertex will also say this edge is suspicious, and the edge will flip. So you use the fact that the expander, you can't have too many errors kind of clumped in the same area near the same vertices to make this algorithm work. This is very imprecise, but just want to say that one of the properties of expanders is that they have very good isoparametric behavior. If you have a small set of edges or vertices, they must kind of spread out, and this helps the decoding algorithm. Okay, let's go on. Okay, so that was application of expander graphs, one-dimensional, it's still not high-dimensional, to error-correcting codes. Here's another, this is the last one I'm showing, application of expander graphs to something in computer science. Here I'm talking about mixing of random walks. why would we care about mixing of random walks? Here is one example that people often give. Suppose you want to sample a random configuration of something. For example, maybe it's a physical system. Here's the best example that people like. Suppose you have a deck of cards and you want to have a randomized deck of cards so that the permutation of the cards is completely uniform. Okay? So how do you get that? How many different permutations does a deck of cards have? A lot, right? 52 factorial, that's a huge, huge number of permutations. So you cannot list all of them and choose one at random. That's infeasible. Instead, we do something else. We shuffle the cards. Okay? Why does shuffling the cards give us a good permutation? Well, I thought a reasonable thing to do. So one way to think about it is to think of the graph underlying this situation. So you draw a graph where each node in the graph, it's not a person now, it's a permutation of the deck of cards. Okay? So you have here 52 factorial nodes in this graph. Of course, we're not really thinking about this graph or drawing it anywhere. It's just in our minds. And from every node here, we have a transition to another node if one of the shuffling steps moved me from this permutation to that permutation. Okay? And now if I'm able to analyze this graph and show that it's an expander, it means that if I start a random walk, I start with some permutation, I don't know which one, and I start a random walk. A random walk means I look at all the possible neighbors and I choose one at random. And then I look at all the possible neighbors and I choose one at random. And if the graph is an expander, it means that I need to walk very few steps and I reach a uniform location. So that's why when you shuffle cards, you only need to do a few steps and you're all good. Of course, this is just an example. There are many situations where you want a random configuration. And we'll reach this again in the talk because we'll show the same kind of thing for high-dimensional expanders. By the way, if you have questions, please feel free to ask. Okay. Okay, so expanders, there are many, many other ways that expanders occur in computer science. I don't want to spend the whole talk on this. But of course, it's important to ask, are there even expanders? When people first thought about this idea of a graph that has, every vertex has very few neighbors, but somehow is well connected, they didn't necessarily believe that it exists. But it does exist. Actually, random graphs are expanders. And as we heard, there are deep results in number theory and group theory that are used to construct explicit families of expander graphs. These are the famous Margulis expanders, and Lubotsky, Phillips, and Sarnak constructed these optimal expanders called the Ramanujan expanders. And this is a very celebrated result, and a lot of further works use these constructions because even though proving that they have the properties is very difficult and requires deep mathematics, using this graph is very easy because the description is so explicit. You get a Cayley graph, you get a bunch of generators, so it means it's very easy for you to compute, if you're here in some vertex, who is your neighbor. It's super easy, so it's very useful. Later on, a few years later, Reingold, Vadan, and Victorson came up with an elementary construction, no number theory, and so on, that gives excellent expanders. So we don't even need all this deep math, but somehow the route to getting these explicit objects went through this theory. Okay, so I do want to talk a little bit about the construction of LPS, Lubotsky, Phillips, and Sarnak, because it leads us to the high-dimensional expanders. So how did they construct their expanders? The first thing you look at is this picture. It's the infinite tree. You start here, every vertex in this picture has 3 neighbors. And then you move to a neighbor. This guy also has 3 neighbors. And then you move to a neighbor. Maybe in the audience you don't know how difficult what I'm doing is to do this, but maybe I'll stop. Okay, so anyway, it keeps going like a fractal, right? It goes to infinity. Every guy has 3 neighbors, 1 in the back and 2 in the front, and you keep going. And this kind of object is actually a very good expander in the sense that if you choose a set of vertices, you see that there's going to be many, many, many outgoing edges, and that's what makes an expander. However, it's not so useful because it's infinite. So the main idea was to create a finite object that still has these properties. And the way they do it is by taking a quotient. So this was the LPS construction. It's a quotient of the infinite tree. And really, it was, as I said, was a tremendous success with many, many applications. Okay, so I guess the way I heard the story from Alex, they thought, oh, wow, this was very good. Then some more theorems were proven for the higher dimensional analog of the infinite tree. What's the higher dimensional analog of an infinite tree? So there are many different ones. And this is the one that they were interested in. It's called the affine building, the Brotitz building. Just like in the tree, you have a vertex, it has some edges, and then from there you have some more edges. Here you have vertices, you have edges, and you have triangles. And if you're in higher dimension, you also have 3 simplices and 4 simplices and so on. And in this picture, you see every edge has many triangles on it, like many pages. But then every triangle, from any one of its 3 edges, there's more triangles, and so on and so on. You get this infinite object. What can you do with it? So Lubotsky with Samuels and Vishne, already 15 years ago, said, let's do the same thing. Let's try to find a quotient of this object in a way that we get similar properties that the infinite object has, but it will be a finite object. It's not only one finite object, right? It's an infinite family of objects whose size grows to infinity. That's what we really are interested in. Okay, so this is what they did. They took quotients of the Brotitz building, explicit ones, and they got this thing that they called the Ramanujan complexes or high-dimensional expanders. Okay, so really this is a beautiful construction. It uses very deep mathematics, and it has some really fascinating properties. The one problem is it's very inaccessible, or maybe I wrote here, it's somewhat inaccessible. Unclear if somewhat is stronger than very. But anyway, if you're not in the know, if you're not like a number theorist or someone who works on these objects, it's very difficult to even understand what the paper says, what is the construction, what properties, how can you use it. It's very unlikely that a computer scientist will look at this and say, wow, this is exactly what I need. Now I'll go and take it and build things for it. Okay, it takes time, these things. But here is one thing that you can already see that works very well on this object, and this is random walks. Instead of graphs, now we also have triangles, so we can talk about random walks, not only that go from vertex to an edge to a vertex to an edge, we can go from a triangle to an edge to a triangle, or from an edge to a triangle to an edge. So there are higher dimensional random walks. And in this object, in some way that can be made precise, these random walks are as fast mixing as possible. Okay? It turns out that even the finite quotients maintain this property. They're really excellent mixing. That's an interesting property. Can you use it for something? Okay. Before I continue, I just want to say, I don't want to define exactly high-dimensional expanders because I don't know the definition. I think it's a new area. It's still evolving. Every few years, some other object that's not exactly fitting the old definition comes up and is also interesting. So I just want to give you the sense of what's going on here. We moved from graphs to something that is a higher dimensional object. And in this case, the object that is most popular these days is this simplicial complex. Simplicial complex, let's think about it, a graph with triangles. Okay? And as we talked before, we are now looking also at random walks on higher dimensional faces. So not only on vertices, also on edges and triangles, so on. And here is the first property that actually, I think throughout my entire talk, this will be the property that I think captures most of the interest from computer science in these objects. Okay, so this is a very compelling thing, this local to global property that high-dimensional expanders have. And I want to talk about it a little bit and see how the applications that we already have use this property. Okay, so local to global from links to the entire complex. So what are links? When you have this complex, for example, this Lubotsky-Samuels-Vishne complex that's super complicated in my mind, how are you going to understand it? So one thing you can do is let's look at it piece by piece. Let's kind of think of it only one link at a time. So what is a link? Here, I tried to draw some simplicial complex. So I have triangles, and they're linked together, and there's more and more of them. And the link here is, let's look at the link of a vertex. So you have here a vertex. It's highlighted in pink. And the link is a little graph. The vertices are the neighbors of this vertex. So you see there's 5 vertices that are neighbors. You know what? I'm really not so good with this thing, so I use this instead. Okay, yeah. Okay, so here's my vertex. I'm now talking about the link of this vertex. So this vertex has 5 neighbors, right? So I have 5 vertices in my link. And every time there is a triangle touching my vertex, this becomes an edge in the link. Okay, so in this case, the link is just a circle, a cycle of length 5. That's the link of this vertex. Of course, you can also look at the link of this vertex and the link of that vertex, and so on and so on. So really, you can look at the entire structure of the complex link by link. And here is a theorem by Zahar Oppenheim, who is speaking tomorrow, I think, about something a little bit similar to this theorem. And really, people that are in the know say that this already kind of is in the spirit of a much older theorem of Garland from 1973 that also used something about the expansion of the links to show that the entire Laplacian is connected, meaning that the real cohomology vanishes. But what did Oppenheim prove? Roughly speaking, he said, if each one of these links, for every vertex in your complex, the link is an expander in some quantitative way. It's not enough that it's connected. It needs to be an expander in a quantitative way. And the entire thing is connected. Then the entire graph that you see here, and now you don't have to think about the triangles anymore. Just think about the vertices and edges. The entire graph becomes an expander. Now, this is the first theorem of this kind that I've seen, because as Alex also mentioned, when you have a one-dimensional graph, you can have 2 graphs that locally they look the same. The local neighborhood of a vertex is always like a tree. One of them will be a great expander, and the other will be a terrible expander. So for one-dimensional objects, such a theorem is false. I mean, maybe there's a way to rephrase it so it's true, but I don't know how. But for 2-dimensional complexes and above, local behavior, local expansion immediately implies global expansion. That's a very, very beautiful statement, I think. Okay, it's very beautiful. It's also useful for some specific concrete computer science application. The application would be solving a 30-year-old conjecture. Okay, so here we're talking about fast mixing of some specific random walk that people have been conjecturing that this random walk mixes for a long time. It was finally resolved by Anari, Liu, of Esgaran, and Vinzant 2-3 years ago. And what they showed is, this relates to the question I was talking about with the deck of cards. Instead of wanting to have a deck of cards with a perfect permutation, you want a random configuration of something else, of a matroid. So let me not talk about matroids in general. Let's talk about one specific thing. Suppose you have a graph, and it's connected, and you can think about a spanning tree in this graph. Okay? There are many different spanning trees in a graph. Well, if it's a tree, there's only one, but if it's a richer graph, there are many of them. And you are interested to find a random spanning tree in this graph. Of course, a graph can have many, many spanning trees. How are you going to do it? So what they suggested is, what can we do? We start with some spanning tree, and we can do something like a card shuffle. From one spanning tree, how do I move to another spanning tree? Well, I'm going to add an edge. This edge is now going to close some cycle in the spanning tree. So now I can erase some other edge, and I again got a spanning tree. And this gives me a transition from one spanning tree to another spanning tree. And then I can keep going and do another one and another one. And maybe after some number of steps, I reached a random spanning tree. Who knows, right? So how would you prove that? You need to look at the graph whose nodes are the different spanning trees and whose transition is what I just said, and analyze the spectral behavior, for example, or analyze how well this graph expands. Oh, this is exactly what they did. What they showed is that really, this is not just a graph. What this is a higher dimensional object. It's better to think of these trees not as vertices of a graph, but rather as faces in a simplicial complex. And now think of the walk not as a walk from vertex to vertex. Think of as the walk as something from n-1 dimensional face, because this is how many edges a tree has, to another n-1 or n-2 dimensional face. Okay, so if you think about it this way, it's natural to think of links. You want to analyze this random walk on a high-dimensional thing, look at links and see how the walk behaves there. And if it's very well expanding there, then you can use this trickle-down theorem or some similar theorem and prove that the entire thing mixes. And this is exactly what they did. Actually, it turns out that analyzing this random walk on the links is easy. It's not at all difficult. So once you get all these ideas together and you understand how to break a global random walk into small pieces, everything else falls into place. Okay, I have a picture here. I guess this picture is supposed to show the transition. This is one node. It's one spanning tree. So I guess I don't know if you see the difference between the black and the blue. The black is the spanning tree. Now we add this extra potential edge to the spanning tree, and maybe we remove this one. And what they proved is that this walk converges in polynomial time in the size of the graph, which is logarithmic in the size of the graph. When I said polynomial time, I meant in the size of this graph, which is really logarithmic in the size of the Markov chain.
So in the theorem, you mean you sample a random basis, even matrix. That's
Thank
the
you.
extension.
The random matrix. This is one basis of the matroid, this spanning tree, right? And then move to another basis. Another example of a matroid would be a set of linearly independent vectors, right? Okay. Okay, so that was another example, or actually maybe the first example we saw of a surprising application of high-dimensional expansion and thinking about this high-dimensional expansion for solving some problem in the mixing of Markov chains. And you see that the idea lying at the heart of it is this local to global. We analyze a global object by breaking it down to small local parts. Okay, now I want to go back to error-correcting codes and see whether high-dimensional expanders can be used there. We saw before that expanders are useful for error-correcting codes. For example, in the Sipser-Spielman construction, you use the expanders, well, for several things, but in addition for decoding. What can you get if you use, instead of an expander, a high-dimensional expander? So we had a program I guess, summer of 2019 at the Simons Institute in Berkeley. And this was a program about codes and high-dimensional expanders. And in this program, you see even the graphic that the graphic designer made for us, which I really liked. He showed how there's an underlying skeleton, which is this expander, or maybe it's high-dimensional if you look at the triangles. And on top of it, you put the bits. Remember in the Sipser-Spielman code that we talked about, the bits are on the edges. But here, maybe the bits will be on the triangles or some higher dimensional faces. So that was the hope back then. And there were a few works that kind of pushed these ideas further. So one work that we had with Harsha, Kaufman, Livni Navon, and Tashma, we showed that if you construct a code on a high-dimensional expander, then you can list decode this code. So I don't want to go into exactly what list decoding means. It's some stronger paradigm than just decoding. You can tolerate much more errors. And the idea there was list decoding is more difficult, so you break the received word into parts according to the links of your high-dimensional expander or according to the local pieces, whatever they may be. And then you list decode each piece separately. And because the pieces are so small, maybe you can do it exhaustively, because it's just 20 bits, you go over all possibilities, and then you stitch everything back together. So that was this work. Later, in 2 papers, I combined a set of authors. They improved this work a lot and generalized it. Used it to firstly find an algorithm that solves some family of problems called CSPs. These are important problems in computer science called constraint satisfaction problems on high-dimensional expanders. And then they used this idea that they can solve CSPs on these objects to decode codes. More than that, they realized they don't need high-dimensional expanders in the very sophisticated definition that comes from the Brotitz building. Actually, they need a weaker property called splittability in these papers, which is a kind of high-dimensional expansion. Maybe it's weaker than the number theoretic one, but it's still strong enough for them to solve CSPs. You know, maybe for you these are just 3 letters for some of you, but CSPs are really many of our favorite problems, like 3-SAT or max-cut. A lot of the problems that we care about are really a kind of CSP. So the fact that you can solve a CSP on this family of problems is pretty impressive. They even managed to do this and to decode codes that have almost optimal parameters. Okay, I'm not going to go into these details, but I thought that was quite an impressive work. One thing that bugged me, for example, when I learned about this work, was that they were solving CSPs on these high-dimensional expanders, but we were thinking that actually it's difficult to solve CSPs on high-dimensional expanders. We were thinking that actually you can use these high-dimensional expanders to prove hardness, or that CSPs are hard. And they kind of contradicted each other, but then we kind of joined forces and we realized that there's some subtle issue. How exactly do you define the CSP? Is it on the edges or is it on the vertices? And this subtlety is all the difference, and we did show hardness. The CSPs are both easy on HDX and also hard on HDX, depending exactly on how you prove them. So I think that's interesting, but it's kind of a side comment. So I guess maybe the takeaway from this slide is that high-dimensional expanders can be used both for proving hardness and for algorithms in this context. Okay, another computer science application or coding application is the C-cubed error correcting codes that Alex was talking about in the previous hour, but I'm going to describe them a little bit or just describe the problem. So going back to error correcting codes and what we talked about, when you get a message, someone sends you an encoded message, what you get is called a received word, and you want to know how much noise happened to it. How much noise does this string already have? You can just try to decode the string and see what happens. Maybe you'll fail, maybe you'll succeed. But maybe there's a better way. Maybe there's a faster way to kind of quickly see if too many errors happen, just ask the sender to send it again, instead of wasting time trying to decode it. Okay? So this is really the idea of locally testable codes. A locally testable code exactly allows you to check ultra fast. Instead of trying to decode and wasting all this time, just tuck, 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 select a few random bits and decode. Where does this come from? You can think of locally testable codes as a special case of property testing, related to what Henry was showing us in the morning. Property testing in general cares about the relationship between a global property, global objects, and how they look like from local views. Okay? And this is kind of the theme that's repeating again and again in this conference and also in in the examples that I'm looking at. So in fact, I think the first connection between high-dimensional expansion and computer science is this work by Kaufman and Lubotsky, who showed that cocycle expansion, systolic expansion, is syntactically almost the same as some kind of property testing result for cocycles or coboundaries, whatever that means. It just shows that this specific notion of high-dimensional expansion is equivalent to property testing for this specific property. So that's interesting already back then, showing us that there is a relationship between these things. And okay, several years later, we constructed these error-correcting codes that have this property tester. So this is the C3 problem, was the problem of constructing error-correcting codes that are good, namely they have constant rate and distance, and at the same time they have a property tester. Okay, and you can kind of trace this back to this early work of Kaufman and Lubotsky, but I guess Alex was just telling me that a couple of years ago in the public lecture that he gave in this conference, he gave this as a kind of a dream. Maybe we can use high-dimensional expanders and get these codes. So what's the idea? How do we do this thing? Instead of using just an expander graph, we use a high-dimensional expander. So remember in this, I guess I don't have space here. Remember in this expander code, we were putting the bits on the edges of the graph. Now, if we have a higher dimensional expander, we have higher dimensional faces. So in fact, in this work, we don't have triangles, we have squares. It's a square complex. It's very similar to a simplicial complex, except the two-dimensional faces are squares. And we put the bits on the squares. And then everything else is kind of defined analogously. And the main idea is that just like previously, we lifted the error resilience from property that happened around the vertex to the entire construction. Now we lift both the error resilience and the local testing from the links to the entire object. So again, we use this kind of local to global. We define a code, make sure we have some nice property on the links, and then the expansion allows us to lift it globally. Okay. Oh, I have it here again. Okay, so in this slide, I guess I wanted to emphasize this. In the one-dimensional expander codes, we lifted the local redundancy to global distance. And in the new two-dimensional expander codes, we lift both the local distance, so the local distance and the extra property of being locally testable globally using the two-dimensional expansion. Okay. And you have this nice thing that the properties of the code propagate from local pieces, the links, to the entire code. Okay, now where did this idea of locally testable codes and having a code with a property tester, where does this come from? Shannon certainly didn't care about this or didn't think about this because the kind of codes they were playing around with, random codes, will never be locally testable. So it's not an idea that's natural to even think about. And the way it came about is through this theory of probabilistically checkable proofs, PCPs. And this is kind of a very developed theory by now in computer science. And what is it about? So this is kind of the famous picture that I have in mind. It's Madhu Sudan is the author of this slide. And I guess Henry was more creative and had a new presentation of the same idea. But basically, someone gives you a very, very, very long proof, with 15,000 pages, or maybe Henry had 200 terabytes, I don't remember, for something that you really want to verify, like the Riemann hypothesis. Okay, and are you going to now sit and read all these pages and verify? It would. Errors happen.
I couldn't
If you couldn't do it, then okay. Yeah, it does have a significance. Okay, so wouldn't it be nice if you can kind of browse the thing, read a few random lemmas? If they're correct, you just pronounce the entire proof correct. That would be very nice. Also, when you check your students' exercises and when you do referee, we love to have this kind of random spot checking algorithm work for us. But why don't we really believe it can work? It's because bugs can be very sneaky, right? There can be one bug hidden very well, and everything else looks perfectly fine, and still the entire proof will be false. So proofs are very volatile. Nevertheless, the famous PCP theorem, proven 30 years ago, says that every proof can be encoded so that you can do this thing. You have an ultra-fast random checker or tester for this proof. Okay, this is written in a very non-rigorous way, but I hope you understand the meaning of this. And also, when you understand it correctly, you really think it's almost impossible. How can you encode something so fragile that has one bug and it can break it into a proof that can be checked by just reading a few random bits? It doesn't seem like it's possible to do so. Okay, and yet it is possible. I guess by now, those of us that are working in this area are used to it. So it's not so surprising, but it used to be very kind of mind-boggling.
At least if you believe that you can error correct noisy vectors, you can possibly believe that the same can be done to proofs.
To proofs, yeah. Just like you encode messages, you can encode proofs. Except for proofs, you also encode the computation or the verification. So it's one level above, maybe. Yeah, that's true. Okay. So interestingly, so this statement is already kind of fascinating as a statement about proofs. But also, it has a lot of applications in computer science. So it has a lot of applications in particular to this area called hardness of approximation. I'm not going to go into it, but it's related to the CSPs I talked about earlier. And a lot of NP-hard problems are not only hard to solve exactly, it turns out they're also hard to approximate. And this is a consequence of this theorem. And there are many other applications. A newer real-world application is using actual algorithms for encoding proofs inside cryptocurrency. And kind of instead of, if your cell phone wants to communicate with a server, the cell phone is kind of weak. So the server will do all the calculation, and you just need a proving protocol to make sure that the server is not cheating you. So all these things go into PCPs, and people actually have real-life companies that do these things. It's quite amazing. Okay, I haven't said anything about how do you construct these PCPs. So for error-correcting codes, we said that expanders go into error-correcting codes, and that some codes are based on expanders. For PCPs, PCPs, kind of the classical PCPs, are based on encodings using low-degree polynomials. And there was another kind of construction of PCPs using expanders. But okay, both of them have different pros and cons, I guess. What I want to get to is this slide, which is maybe high-dimensional expanders can give us something new with respect to PCPs. Maybe we can find some construction of a PCP using high-dimensional expanders. I mean, this is completely far-fetched. I have no idea how to do it. I'm just saying that it's a natural thing to strive for, because PCPs, what they do is they take a proof and they encode it into a proof that has very strong local-to-global properties, right? In the new proof, you have many local pieces such that if most of the local pieces are correct, it must be that the entire statement is correct. That's the property of a PCP proof. So it has this local-to-global feature. And high-dimensional expanders, as I've tried to illustrate, have a lot of local-to-global properties, right? We broke a random walk into many small random walks. We broke an error-correcting code into many small error-correcting codes. So it makes sense to look at this connection. Maybe you can use high-dimensional expanders to construct PCPs with better parameters. One parameter that people care about is the overhead. How much redundancy do you need to add? When you encode a message of 1,000 bits, you want to only add 20 more bits. When you encode a proof, you also only want to add a few more bits to the proof to still get all the good features. So that's something that you can hope for. Another thing that I find very interesting is coming up with a PCP that has a more clean construction, like a one-shot construction. The known constructions of PCPs are very recursive and complicated. So this is, I guess, in analogy to the difference between the LPS expanders and the zigzag expanders. We talked about them in the beginning. The LPS expanders, based on number theory, it's very difficult. You need to learn a lot of math to understand why they're expanders. But it's very easy to program them or to understand who is the neighbor of who. In comparison, the zigzag expanders, it's pretty easy to understand why they're expanders, but the exact neighborhood structure is recursive, so it's much more complicated. So I wish, just like that, there would be an analogous construction to the PCP construction. Maybe it will be difficult to prove, but I would hope that it's easy to program, that it's very easy to see which pairs of queries are queried together, and so on. Okay, and maybe constructing LTCs that have this one-shot property, like the ones that Alex was showing us in the previous talk, maybe that's a kind of a first step. It used to be that people thought of LTCs, locally testable codes, as the combinatorial heart of PCPs, because they capture a lot of the properties of PCPs without the computational complexity aspect, just the combinatorial aspect. And it's true even that historically, most of the constructions of locally testable codes came from constructions of PCPs, but not all. And now the question is, can we go the other way? Now that we have a locally testable code that's based on these high-dimensional expanders, can we construct from them PCPs? Of course, this is just a dream, and why not? Okay, let me summarize. We saw that high-dimensional expanders are objects that support local-to-global statements. And these objects give us really beautiful connection between deep mathematical ideas and constructions and questions that are of interest in computer science. I think it's really exceptionally beautiful that some objects that were studied for their own benefit or because of intrinsic reasons, without any horizon of being useful at any stage, are suddenly becoming useful, or at least the ideas around them are becoming useful for completely different reasons. And I think this is something that science sees again and again. And I think in this specific field, we are seeing it every day. And okay, it's very enjoyable. And finally, I want to say that high-dimensional expanders are like a new playground, a new collection of examples. So far, we found some uses for them, and we played with them, and they shed new light on existing objects, like locally testable codes. Prior to this, we only had one family of examples, so we didn't even know which of the properties of polynomials are really important, and which are just, they happen to be there. And now that we have another family of examples, it's much easier to see what's really important and what's not important. So I hope that this family of objects will be useful also for other areas to kind of see maybe new ideas or new applications. Hard to tell at this point.